Hello and welcome to my talk about deep reinforcement learning for uplink, multi-carrier and orthogonal multiple access resource allocation using buffer state information. This was a joint work by me, Yiğit Kiak, and Laurent Schmalen. So today we have increasing number of user equipments with heterogeneous quality of service, for example, conversational video, conversational voice, web browsing, or discrete automation within a cell of a cellular network. So we have many options to allocate the transmission resources we have. An example is a multi-carrier and an orthogonal multiple access scheme. So first of all, we have OFDMA, orthogonal frequency division multiple access, which is really robust against frequency selective fading. So as you can see here, we have two different user equipments and we just can place them next to each other in frequency domains, so they use different frequencies. And additionally, we can use non-orthogonal multiple access, which improves the spectral efficiency. So instead of just placing one user equipment on a certain frequency resource, so here, example, user equipment 1, we can add another one, user equipment 3. For example, we just need to ensure that we can somehow distinguish them at the receiver side. For example, if the signals arrive at the receiver, if we ensure that user equipment 3 has a much higher receive power than the signal of user equipment 1, we can distinguish them. So having this, we can improve the spectral efficiency. However, we also increase the combinatorial space, how to allocate all the transmission resources we have. So the allocation task now is the question how to allocate all the resources to the user equipment to get a maximum system throughput while meeting the user equipment specific traffic requirements, while ensuring that all user equipments are distinguishable at the receiver side. In the past work, we have introduced a Q-learning based centralized scheduler for resource allocation of DMA scenario, and we have shown that incorporating buffer state information greatly improves the performance of the centralized scheduler. So buffer state information is, for example, the age and the size of packets inside the user equipment's buffer waiting for transmission. And as you can see over here, we just feed the buffer state information of UE1 to UEK to a deep queue network, which is our agent. Then furthermore, we hand to the DQN the physical resource block, so the frequency resource to allocate to our decision-making entity, so our deep queue network. And then the queue network tells us which user equipment to allocate to the physical resource block we presented. So the takeaway, just to name it again, is that the inclusion of the buffer state information outperformed the benchmark agents by a factor of 3, and so we just improved the scheduling performance. Now, just a short introduction to deep reinforcement learning before we start to modify our scheduler from the slide before to be able to handle multi-carrier NOMA environments. So in deep reinforcement learning, we have an environment and we have a decision-making entity, which is called agent, which follows these so-called policy pi. The environment is observed and is described by its state, st, which then is given to the policy pi, and the policy pi makes the decision based on the observed state and gives out an action, and the action then is fed to environment and acts in environment. The environment changes and we get a follow-up state, st plus 1, and we get a reward, rt plus 1, which tells us if the action which was chosen by the agent was a good action or a bad action. So the reward can be described as a function of the observed state, of the action that was chosen, and the follow-up state. The goal of reinforcement learning now is to find an optimal policy pi star. An optimal policy pi star is defined as a policy which maximizes the expectation of the sum of the most recent returns, or rt plus 1, and all future returns or rewards. So we have those rewards and they are summed up, and then we scale them by a factor gamma to the power of k, and depending how we choose gamma, we can say, okay, future rewards should be taken into account equally, like the next reward or we just say, okay, we only consider the next reward, or we get something in between. One option now to learn an agent or a policy are actor-critic method. So we have an actor, which is a stochastic policy, for example, so pi with the parameters theta, and given the state S, we get out a vector of probabilities to choose the actions. So having 10 actions, we get out a vector of 10 probabilities, which says, okay, with this probability, you should choose that action. And we have a so-called critic, and the critic is there to estimate how good certain actions are given a certain state. So therefore, what we do is we introduce the action value function, and that's just an estimator of the rewards we will get in the future following a certain policy. As you can see over here, we have the expectation over the policy, and given a certain state S and action A, we just estimate the rewards we get in the future. And having this, we can say for every state and every action, which is the best action, for example, because we can say, okay, this action will yield those rewards in the future. So how do they interact, the critic and the actor? We still have our environment, and the environment outputs a state as t plus 1, which gets to the state. We observe them, and both are fed to the actor and the critic. The actor now decides for an action. So that's our decision-making entity or policy. And the action is passed to the environment, which propagates by one step, and then we get the next state. But the action is also passed to the critic. And then the environment outputs the observed reward for the next step, and that one is only fed to the critic too. And in the critic, we then now can learn the action value function, so the so-called Q function using Q learning. And then with the Q function, we can use the Q function to update our actor to tell our actor which actions were good, so choose them more often, or which actions were rather bad, so don't choose them that often anymore, or avoid those actions. So with a stochastic policy gradient, we can update our policy pi. However, to update it, we require the Q function, Q pi of S and A, and now we need the Q function for every state and every action. Having a large state space or a large action space, this task gets really complex because we need to, since reinforcement learning explores the whole state and action space, we need to visit every state action pair, and that's not feasible anymore if the state and action space get large. So another way to solve this is the deterministic policy gradient. So instead of using the absolute of Q pi, we just sample Q pi for some state action pairs, and then using the gradient, we can update our policy by just moving the probability mass of the stochastic policy to the better actions we observed, and then we just choose those better actions more often. So now back to our multi-carrier NOMA problem. For the state of the art, we now assume that we have K user equipments and M non-orthogonal multiple access capabilities per OFDMA subcarrier. So per OFDMA subcarrier, we have K to the power M ways to combine the user equipments on the subcarrier. Remember the motivation slide when we had user equipment 1 and 3 on one subcarrier. So the traditional reinforcement learning based methods, which relied on Q learning, which we have used in our paper with the buffer state information, they don't work anymore because now the action space gets so large that we can't observe the Q function for all state action pairs. So as introduced before, we can use a deep deterministic policy gradient to learn an agent for the MC NOMA scenario, which was already done by this paper over here. However, they didn't incorporate buffer state information. So our task now was to take this work and extend it by the buffer state information, which we have proven to be beneficial, and then check whether the incorporation of buffer state information improved the agents or not. So for our system setup, which describes the environment, we used the Nokia wireless suite, and now we have N is the number of orthogonal physical resource blocks, so of DMA capabilities. We have M NOMA capabilities per physical resource block. So M users we can put in a non-orthogonal way on these physical resource blocks. We have K number of user equipments, which we can allocate to the different resource we have. And all the user equipments have alike transmit power. So, which means they all have the alike transmit power, but on the other hand side, as explained before, we need to ensure in the receiver that they are distinguishable by the received power. So the agent needs not only to find the way that we meet all the traffic requirements for every user equipment, but also to find a way to only combine user equipments with sufficiently distinct path gains or path attenuations so that their received powers are sufficiently distinct so that at the receiver side we can distinguish them and then we can get the data of them. The state space of the environment is described by QK, so that's just indicator for the quality of service class, which we introduced in one of the first slides. Then we have a channel quality indicator, which indicates the channel quality index of user equipment K. We have L buffer slots per user equipment, and then with the L buffer slots in each slot, if there's a packet waiting for transmission, we have the size of the packets and the age of the packet inside this buffer waiting for transmission. So one problem we faced was the sequential problem of the NOMA allocation. So first of all, we extended the action space by 1 because we said, okay, we can leave a NOMA capability empty. So for example, if user equipment 1 gets the first physical resource block, and then maybe it's beneficial to leave the second NOMA capability empty, so that just user equipment 1 can transmit on this physical resource block without any distortion of other user equipments. So we have the action space, which consists of K plus 1 actions. So assign user equipment K or leave a resource empty. Now, another problem we face is that the buffer state information is only updated after all NOMA resources of a physical resource block are allocated, which means if we allocate the first user equipment to the first NOMA capability, and then we do the decision for the second NOMA capability, but we don't update the buffer state information, then the agent thinks we did, hey, user equipment 1 has data to transmit, and he wants to assign the second NOMA capability too. However, we're already able to transmit the data with the first NOMA capability, so it doesn't make sense to assign the second NOMA capability to user equipment 1. So to avoid that, we just said, okay, we can pass already made decisions to the agent. So if the agent knows for the second NOMA capability what he has chosen for the first one, he can say, okay, user equipment 1 doesn't need further transmission capabilities, so I can just neglect him for this decision. And that's why I decided to just pass the action probabilities of the already assigned NOMA resources to the actor, and that you can see here. So we initialize, or we create a zero matrix X with all the decisions, and then we just pass this one to the actor with the state, and the actor decides for the first NOMA capability. So that's a vector x1, and then we just update our matrix X with the decisions we already made. And this one we feed to the actor again to decide the second NOMA capability, and then we update our decision matrix, and we just continue until all M NOMA capabilities are assigned. Another thing we propose is traffic-based masking. And with traffic-based masking, we just want to ensure that the agent avoids to choose user equipments with empty buffers. So if there's user equipment which has no data to transmit, it doesn't make sense to allocate a resource to this user equipment. And with that one, we just want to boost training a little bit and support the actor using this action masking. And therefore, we just introduce a Boolean, and that one is of size of the number of actions we have, so K plus 1, and it's just the indicator if packets are inside a user equipment's buffer or not. And then if the actor outputs the probabilities of choosing one of the actions. So the probability vector, we just updated probability vector by element-wise multiplication with this Boolean, and then we just normalize everything so we get a probability vector afterwards again. So the whole agent setup you can see in this figure. From the work before, where we had the buffer state information for the OFDMA scenario, we already introduced encoder neural networks, which you may know from the other video. So encoder neural networks just compress the buffer state information we get for certain users. So we have the state 1 describes all information belonging to user equipment 1 up to SK. And then we just compress this data to a lower dimensional space. We just do some random shuffling to avoid learning a bias. And then we feed everything to the deep neural network, which has a softmax as an output function. Of course, we have the zero matrix, initialized zero matrix with all decisions. We feed to DNN2, which gets updated for all the different NOMA capabilities. And we feed the physical resource block to allocate to the deep neural network 2. After the deep neural network made some decision and output the probabilities for taking certain actions, we reshuffle this probability vector. So now we have the correct order of the different probabilities to choose the certain actions. And then we just apply the Boolean masking, which we introduced before, to support the actor. And in orange, you see, so all parts in orange are trainable and all parts in green are non-trainable. So our general setup uses 2 NOMA capabilities and 8 buffer slots per user equipment. And the reward is predefined by Nokia's wireless suite. It's a penalty only. So if we're not able to transmit packets in time and we don't fulfill the latency requirements, then we get a penalty for it. First of all, we take a look at a small environment, which uses 20 user equipments and 10 OFDMA resources. And here you can see the architecture of the network. And we introduce 2 different agents. So the sdef, which is the default agent, and the smask, which uses masking. As you can see on the right-hand side, the default agent has severe troubles in learning. So we have on the x-axis the training episode, so how often we trained the agents. On the y-axis, we have the mean evaluation reward, so how good the agents were after a certain amount of training epochs. As you can see, the default actions is able to learn, but at a certain point of time, he just diverges again and he forgets everything he learned. The masking greatly stabilizes training, and we ensure that the agent converges to a good solution. Now take a look at the large environment. For large environment, we have 32 user equipments and 25 OFDMA capabilities. And we introduce another 2 agents, so the lmask, which is the large environment, agent for large environment, and we apply some masking. And furthermore, we have the ldrop agent, which uses masking and dropout layers. So why dropout layers? As we observed over here, the lmask, which you can see here, learns but isn't stable, and like the sdefault, somehow forgets all the learning at a certain point of time. So we said, oh, maybe that could be overfitting. So we decided to just include some dropout layers. So that's the ldrop agent. And as you can see with the dropout layer, so the ldrop agent has a stable learning and then converges to a stable value. As a last step, we benchmarked our found agents against NOMA proportional fair channel aware agent. So over here you can see all agents we introduced before to compare the methods we proposed. And on the right hand side, we compare our agents, so the ldrop, lmask to the on the large scale, on the large environment to the NP-FCA, and then we compare the smask to the SNP-FCA. And here we just have the box plot with a green triangular depicting the mean and the orange line depicting the median of the 1000 different environments we used for testing. And with the 1000 environment used for testing, we could observe that for the small environment, we only gained 37% of penalty the benchmark got. So, which you can see here, we get way lower mean and medium penalty than a benchmark agent. And for the large environment, we were able to get only 70% of the benchmark penalty. So the NPFCA roughly got 1,600 mean penalty, and we were able to get less than 500 mean penalty with our agents. So coming to the conclusion, we can say that with the deep deterministic policy gradient instead of Q-learning, we enable reinforcement learning for resource allocation in a multi-carrier NOMA scenario. With the feedback of the action probability vector XM, we enable a sequential decision-making, and incorporating the buffer state information improves the performance of the agents by a factor of 4, which we could see in the box plot before. Methods we introduced were traffic-based masking and dropout layers, and both stabilized the training of the agents and ensured converging agents. Thank you for your attention. If you have any questions, you can use the comment section below the video.